Welcome back. And in order not to only talk about the linear regression model, but actually do something with it, let's take a quick look at a example using real-world data. And it's a very common or very popular example. It's the California housing prices example. The data set, it includes, I think it's quite old as far as I know, even a few decades, but as the name suggests, it includes housing values of certain areas in California and some corresponding feature variables with it. So you can find the collaboratory here in the corresponding folder of the course, and it's named something with California housing. As the dataset is so popular, it is available in the sklearn package, and we can download it from here. So if you click on it, then we will do so. And here, first, let's take a short look into the data. And here we can see that we have the median income. As far as I'm aware of it, that's like the income of the people working in a certain neighborhood in California and living there. I think it's, I don't know, scaled somewhat in the thousands or whatever. So I'm not quite sure, but it doesn't really matter here. I guess the higher this value is, the higher the median income in a certain area where the people are living. Then you have the house age. I think all these are average values. So in a certain neighborhood, the average of all the ages of each house. You have the average room sizes, average bedrooms, the population in this neighborhood, the average occupation, I guess, but that's really just a guess. That's something related to rent. So, or I don't know, probably how many people are living there. That's nothing with rent. I guess it's probably how many people are living in the house. And then the latitude and longitude, so the coordinates where exactly the neighborhood is located. And then we have here the target variable, so the median housing value. And I think you should always start with taking a look at some descriptive statistics and just some information of the data. So I always do this here with the head function. You can also do the same with the tail function, and just shows you the 5 first observation or the 5 last observations, depending if you're using the head or the tail method of the data set. Then the info method, I think it's also very useful because it shows you the amount of non-null values. And here we have overall 20,640 observations in the data set. And if we have the same amount of non-null values, then this means we have no missing values for the variable. And as you can see here, this holds true for each variable. So there are no missing values in the data set. And what we also can see here, the type of each variable. And here we can see we only have floating point numbers, so real numerical feature variables as well as the target variable. If you read something here that says, for instance, object are typically strings, strings indicating the category, for instance, of a certain variable. What I also think is quite useful is to take a look at the box plots, because here you can get an idea which variables may be plagued by outliers and stuff like that. So here it's, for instance, maybe the population, or even not outliers. You can also see that this indicates that this is probably a very skewed distribution. Doesn't mean a bad thing for your model, but definitely you should take care of outliers possibly, because outliers, especially for regression type problems, can really have a great impact on the overall results of your model. But let's not go that much into detail here because we just want to get a quick idea how the linear regression model works for real data. Also very, very interesting, I think, are the pair plots. So pair plot is here on the diagonal. You usually have the histograms of each variable. And then here you can see the scatter plots between the variables. So for instance, if we have here the housing value, which is our target variable, then we can see here that there seems to be some kind of relationship between the median income and the housing value. It doesn't really seem, for instance, that there is a relationship between the age and the value of the house. And here maybe yeah, you could guess some sort of nonlinear relationship. But these are just like the binary relationships, right? And our model may also be, yeah, like the, it doesn't, what you cannot see here, how the overall relationship between all the feature variables and the target variables are. So this is just an indication regarding the relationships. And also, if you take a look at the scatter plots between, for the feature variables, then you can guess if there are high dependencies here among them, which could result, for instance, in problems that are related to multicollinearity and stuff like that. More or less the same information, but visualized differently is a heat map. So a heat map, you can see here, there is a certain number range, and here the dark blue corresponds to a value of 1, and here you can then see, like, the darker it would get here, the higher the correlation in a positive correlation, and if it's getting really kind of white, then this is the same as having a strong negative correlation. Also, what I always like for this data set is to do a scatter plot and use latitude and longitude and latitude on the x and y axis, and use the housing value in order to generate the color of the point. So as you can see here, the more red it is, the higher it is, so the more expensive it is. And if you take a look then and can compare this to the how California is lying geographically on a card, so maybe we can find this here. Just housing price in the Kaggle homepage. We have quite nice visualization of that. Just quickly, let me take a look if I can find this. Because I've seen that someone else did this and did this. Okay, here you can see it. This person is doing it in the same way I'm doing it. Let me take a look here. Yeah, this is the same thing again. Okay, I'm not finding it for the moment, so let's just go to Google Maps and go to California. And as you can see here, like, the shape of California is very well matched by the shape that we can see here. And now here where we have red dots, just try to remember these areas. And I guess, like, those are these areas here. So it's like the coastal area of the bigger cities. So the more expensive, like the more close you are to the sea, and yeah, the more close you are to the city, the more expensive it gets. So yeah, I mean, this is really just very specific for this data set, but I think it really shows you what we will find out in a minute, that of course the location of the house is very much what mainly drives its price. Okay, but now let's try to do like a regression analysis as we would typically do it. We will use scaled values of feature variables, and also for the target variable here. Basically, mainly I use the scaling here in order to make the feature variables comparable, that we can compare the effect sizes and directly tell by the effect size which variable seems to drive the estimations that the target predictions the most. And I also split the data set into a training and a test data set in order to estimate the parameters of the linear regression model for some training data, and then have some data left in order to evaluate if this also works well for new and unseen data. And here I use the train and test split function, which really randomly shuffles the data and then picks out 30% for test values, and the remaining fraction is used for training the data. You should be careful with randomly or randomized shuffling and then splitting the data, for instance, for real financial data, because this is often often includes a high degree of temporal dependence, and just mixing up the data and not taking care of time systematic effects may have a negative impact on your results. So just to create some awareness here, but for this data set we can simply do it like randomly shuffling the data and randomly draw 30% of the data for test data, and the remaining is used for training. Now here we train our scalars, which means we use the empirical estimates of the expected value and the standard deviation, and then here we transform them, and here we have the scaled values. Again, it sometimes makes sense because we will use the scaled values for estimating our model to again take a look at the box plots here, and maybe if you're late at a later stage, you could try different scaling methods in order to rule out these more extreme outliers for your feature variables. But for the moment, let's do it like this. And now it gets quite easy. So we import the linear regression model from the sklearn package. Here we define it. Here we train it using the scaled training data. And here we calculate the feature importances. So basically what we do is we divide each effect by its normalization, and the values of the parameter estimates are normalized to sum up to 1 by using the sum of the absolute values for the parameter estimates. Now let's just take a look at the results, and what we can find here is that the median income has a positive impact on the house price. So the more the people earn in a certain neighborhood, the more expensive their houses seem to be. Of course, there's really some serious question of causality here, but I think that matches your intuition. Now, and then here we can see that we have again a great impact of latitude and longitude. The sign kind of I don't know exactly where to look at. So in which direction on the map we need to go for increasing latitude and longitude. So not sure about the sign, but probably will make sense. But especially when we take a look at the absolute values here, then this has almost an equal impact as the money people earning in a neighborhood. So most important aspects for the price of the house is where it's located and if it is a fancy neighborhood, so to say. And of course, maybe the house size, which can be approximated by the average bedrooms, is also quite important. So the more bedrooms we have, the higher or the bigger the house, so the more expensive it gets. Okay, and so quite makes sense to me, the results here. So now we can evaluate the quality of our predictions. We can do this, for instance, by the R-squared metric. So what it basically does is it takes a look at here the deviations between the actualizations and the predictions, sums them up, and that's why we're using the squared values. Same is done with the naive estimate here, which is just the average value of housing prices in the training data. And this metric is defined in a way that the closer it gets to 1, the better are our observation-specific predictions, which are determined here, in comparison to a naive prediction, which would just use the average of all house prices to make a prediction for a house for the value of a house. And I evaluate this here with for the not the scaled data, but for the true data. And here we have comparable values for training as well as testing, and of approximately 60% here. And we can also, evaluate the quality of our predictions visually by comparing the predictions versus the realizations. So in a perfect world, all values should be here on the diagonal line with a slope of 1 and going through the origin. And as you can see here, this is not the case here. Obviously, in reality, this will never be the case. Usually, we will never find a perfect model. But especially when we take a look at this visualization of the prediction capability, we can see that obviously something is going wrong here. So the real prices are truncated at 5. And if you ask your favorite statistics friend or partner, then he will tell you that using a traditional regression model for truncated data will cause problems for your parameter estimates and will distort the parameter estimates. So that seems to be the case here. And that is why we seem to systematically underestimate the prices. We overestimate the prices, sorry, for the more expensive houses, because here we have the less expensive houses and everything seems to be quite okay. Same holds true here. But then here in the upper area, we always have more points in, the upper part of the plot, which means, for instance, here, if we have a true house value of 4, we really underestimate. So we have a true value of 4, or I don't know, let's go here, and then we have like more lower valued predictions. And this makes sense with respect to the truncation. So we seems to be not distorted, so we do not over predict, but I would say under predictive. I don't know if that really is a word, so let's write it like this. Okay, so this is a short example how you could conduct or do a regression analysis and get an idea if your model is okay, if something's going on here. So here we found out something is going on. We have truncated data, so in reality we probably should do something to deal with this more appropriately from a statistics or from a modeling perspective. But that's not really our focus here. And also we have seen how we can find out which variables seem to be most important. We already had this intuition before taking a look at the results here, but basically they confirmed what we've seen before when taking a look at the descriptive statistics, as well as, or not the statistics, but at the visualizations that we've seen before, and maybe also that's the intuition that you already have when it comes to what prices, like what houses costs and what probably is likely to drive the house prices. Usually it's rather the location and not really just the quality of the house. Okay, so as always, be my guest to copy this code, play around with it. Maybe if you want to give me feedback, if you're finding any mistakes here, or if you find something could be done more appropriately. And that's it for this video. Take care and see you in the next video. Bye bye.